All right, on to the next piece of thermodynamics. And so this ties to an idea someone asked me about. Well, all right, we're calculating all this entropy change, the delta S, last week. Well, what's it good for? And so this week we're going to try to take it and make use of the delta S as combined with the old delta H that you learned back in Gen Chem 1. And we're going to actually try to use it to do a thing. And that thing is going to be predicting the spontaneity of reaction. And so I think we kind of ended with this last week with talking about delta S and the calculation using that table G in the back of your textbook and how similar it is to calculating the delta H that we did back in Gen Chem 1. So the sum of the products minus the sum of the reactants. Delta S works the same way. Sum of the entropies of the products minus sum of the entropies of the reactants. I hope that you noticed when you're looking at that table that there's delta H listed, there's delta S listed, and there's a third thing. There's a delta G listed, and we're gonna start using that delta G today. And so, tying back to the second law of thermodynamics, right? We think that if a thing's going to happen, if a reaction is going to run, then if it's going to be spontaneous, that is to say, then the entropy of the universe needs to increase because of that reaction, right? So simple then, we need to see if a reaction is going to happen. We just measure the change in entropy of the universe. But, well, you can't really measure the entropy of the universe. So we have to limit ourselves to measuring what we can get to. And so that's why we have to go through all these shenanigans with this new concept of free energy here. It's a created concept. 1860s, Josiah Gibbs, the G in Gibbs free energy. I think he's at Yale. Read a neat history snippet that he was the first, at least in the U.S., maybe, I don't know if everywhere, but at least in the U.S., the first PhD in science. Before it had been like natural philosophy and stuff like that. But he's turns it into a mathematical science at Yale, and then he stayed there for a long time after that. But this is the idea of using the maths to get at what's going on with spontaneity. And so this is going to be our super important equation, and no holds barred. This definitely needs to be on your notes and any cheat sheets that you make, stuff like that. Delta G, that's this new thing that we're going to talk about, Gibbs free energy. Delta G of a reaction is delta H from Gen Chem 1, subtract the delta S that we just did last week, multiplied by the temperature at which the reaction is going to occur. So this guy's going to be extremely important going forward. All right, so back to our second law of thermodynamics. So we know that the delta S of the universe needs to increase. That's the greater than zero part over here. Delta S of the universe needs to be a positive number for a reaction that's going to occur. And further, that the delta S of the universe is the sum of the delta S of our system plus the delta S of everything else, what we call the surroundings, right? Well, okay, but we can't go measure the delta S of the universe. We can't measure the whole universe. Now, we can, and we just did this last week. This is what we spent that time doing the delta S of our reaction. So we can at least find a numeric value for this term. Now, we have to figure out then the delta S of everything else. Where's the delta S for the surroundings? Where are we going to get a number for that? So what we're going to do is we're going to look at that delta S as being the delta H coming off of our reaction. Now, be careful here. We're going to flip a sign because we're not looking at the delta H going into our chemicals anymore. We're going to be looking at it oppositely. So it's the delta H coming off. So here we are again. We're going to do some algebra shenanigans with this. So we have delta S of the universe equals delta S of the system plus delta S of the surroundings, and that has to all be greater than 0. But now we've said, let's see, we know how to measure the delta S of the system. That's what we spent last weekend. And now we're going to talk about that the delta H coming off of, and the off of gives us the negative, off of our system, but it has to be divided by T. And here's why. If you add a little bit of heat to a system that's really, really cold, let's say close to absolute zero, if you add just a little bit of joules of heat, it's going to change the entropy of that system drastically. But if you take a system, let's say surface of the sun, that's already super, super hot, and you add that same amount of heat to it, it's probably not going to notice. So the temperature that something is at already matters. So we're going to take the delta H coming off of our reaction, and we're going to divide by the temperature at which the reaction is occurring. Okay, now algebra shenanigans again. I'm going to multiply this whole thing through by T, right? So when I do that, this T on the last term cancels out, and we get a T on this term and a T on this term, okay? Then I'm going to multiply through by the negative here. So there's my negative going through. And then rearranging. So this is what we were trying to get, right? We wanted to know what the delta S of the universe is going on here, right? Well, now we have a way to calculate. We've got the delta H from Gen Chem 1, and then we're going to subtract temperature times the delta S that we did last semester, last week. I'm sorry, last semester is the delta H. Last week was the delta S. And so that's going to give us this value, and now we're going to name it a new thing. We're going to name it the delta G. So the delta G is the delta H right there. Subtract, because we're looking at it from the opposite direction now, subtract T times the delta S of the reaction. We're going to use that, look at the delta G of a reaction. And so we'll talk about that as this term free energy. It can be a little confusing sometimes, but a lot of folks, most everybody uses the term free energy. So get used to using the term, but what we're doing with it is we're predicting spontaneity of the system using it. And here's our criteria, right? So we wanted to know what happened in the universe, right? Well, okay, now we have this delta G replacing what's going on in the universe. If the delta G is negative, if it's less than 0, then we're going to say that, yep, the reaction is indeed spontaneous. However, opposite, if the delta G is greater than 0, we're going to say, no, that's not a spontaneous. It's not going to run that direction. It's going to actually run the other direction. And then we're going to spend some time talking about this special condition where delta G is precisely 0. And it turns out that that whole stuff we were doing with equilibrium back on exam 2 is tied back to this condition where the delta G ends up exactly at 0, and you have an equilibrium condition. All right, so looking back, tying back to your stuff from Gen Chem 1 again, you know that if delta H is less than 0, you have what's called an exothermic reaction, right? And a negative delta H will contribute to giving you a negative delta G. So having an exothermic reaction does help to explain spontaneity. However, now we have the whole equation here, minus T delta S. We know it's not the whole story because you need a positive delta S. So now you have an interaction between these two things to see which one wins to give you an overall negative delta G. And we'll practice calculating some of that in class to get you used to checking. Also do remember that temperature matters now on the delta S side, but not on the delta H part. And so, you guys know I look at things graphically a lot of times. So here I have in the pink area up here, delta G greater than 0, right? I did steal this graphic from your textbook, so you can see what all they might be talking about. It. Just looking at it the way I would, the pink area up here is delta G greater than 0, so we have a non-spontaneous reaction. And that can be because delta H is greater than 0 and delta S is less than. So if delta H is positive and delta S is negative, well, you can guarantee then there's no way for your delta G to end up as a negative value in the case that delta H is positive and delta S is negative. Down here, I'm going to jump down. The green line down here is in case where delta H is a negative value and also delta S is a positive value. So you'll have a negative value subtract a positive value. That's guaranteed to be a negative value. Okay, so the red condition is always going to be non-spontaneous. The green condition down here is always going to be spontaneous, delta G less than 0. But then you have these other two cases where, in this case up here, both delta H and delta S are both positive. In this case, delta H and delta S are both negative. In those two cases, you've got to run the calculation. You can't tell without seeing which term has a higher absolute value whether the overall is going to be positive or negative. So you've got to run the calc to see if it's going to be spontaneous or not. So another thing you could do with that is you could take and you could find where, for those yellow lines on the previous page, where spontaneity flips from spontaneous to non-spontaneous. And you could find that temperature by playing with the algebra with that. And that would be the temperature at which your reaction would be at equilibrium for the given conditions. So you find that delta G equals 0 temperature. And you just do that by taking, well, if we want delta G equals 0 here, right? Replace that with 0. Now you've got delta H equals, 0 equals delta H minus T delta S. If I were doing the algebra here, I would add the T delta S to both sides, and then divide by the delta S and get T equals delta H divide T delta S. Or divide delta S, the T stays over here. All right, one final concept we need to talk about with Gibbs is the conditions that we set these. All right, so these tabulated values, back to your textbook again, Appendix G, are all set at what we call standard conditions. Okay, so we'll talk a little bit more about what the standard conditions are. Also, I wanted to point this out because I don't want any tricks to catch you. And I see this calculation happen a lot of times. So delta H in the tables almost always shows up as kilojoules per mole. All right. Delta S, though, in the tables, they're going to list as joules per mole K. All right, so K is because you got to multiply by temperature. That part's fine. You can handle that. But they'll do joules per mole for S, and they'll do kilojoules per mole for H. So just be careful with that and make sure that you either convert to kilojoules per mole to start with or convert before you subtract. I don't want it to trick you. And there's a snapshot from the table in your text, and there you are, joules per mole K, right? And delta G is in kilojoules per mole, and delta H is in kilojoules per mole. Now you're going to calculate these the same way you did with the delta H's, where you're going to add them up, stuff like that. Just remember that we're defining this for a standard state. So for aqueous species, we're talking about a 1 molar concentration. For pure elements, 1 bar, 25C, always that 1 mole of the substance. So if you're gonna multiply, like the reaction I have down here, right? So we're combining to get H2O. Well, we got 1 mole H2O. Cool. So we would look up the H2O part. And then just remember, if you've got like a coefficient, here I have the 1/2 and a 1 in front of the H. And a lot of y'all have asked, why would I ever use fractions to balance an equation? Well, here's an excellent example of why I would. Because now I can look up the H2O in the table. It's going to be negative 237.1 kilojoules per mole. But I'm going to have to multiply 1/2 times the value for O2. But the key is that O2 is defined as standard conditions. That's how oxygen's going to come to you at standard conditions at 25 C, 1 atmosphere pressure. It's going to be in the form of an O2 gas. So its delta G is going to be 0. Similarly, the H2, delta G is going to be 0. Well, okay, by using the 1/2 and keeping the H2O coefficient as a 1, I'm multiplying the negative 237.1 times 1 and multiplying 1/2 times the 0, which is still 0. So that's why you might balance an equation using fractions, is to keep your maths a little easier so that you're using the 1 where it's most beneficial to you. So your overall delta G formation for H2O at standard conditions is negative 237.2 kilojoules per mole. And we can use those formation calculations just like we did back in Gen Chem 1. For delta H formation, we can use delta G formation the same way. Products minus the reactants. I hope that you did go back and review the delta H from Gen Chem 1 like I suggested, because all the problems for that are gonna look very similar to problems you're gonna do for the delta G. So you want that practice going in. It works. This equation works for reactions that are at standard conditions, 298 K, and one. I think they do it in bars. It might be in atmospheres, but I think it's in bars. Those, for your purposes, you probably don't care about the difference. They are slightly different calculation-wise, but I don't intend to use a trick like that. So for your purposes, I think here you can consider 1 bar and 1 atmosphere to be the same thing. Remember, the delta G formation of any element in its most stable form at those standard conditions is going to be defined as 0. So if we're talking about using oxygen, it's going to be an O2 gas. If we're talking about using, say, carbon in one of those, well, what's its condition at your standard, where you're a stable chemical? That's going to be at 1 atmosphere or 1 bar of pressure, and it's going to be at 298 K, right? So what would carbon come as? It would come as graphite. So graphite's delta G formation is going to be listed as 0 in the table, so you can look them up that way. But not everything happens in chemistry at standard conditions. So we have a way to calculate things that are not. For instance, I don't really want all of my reactions that involve H plus to be run at a pH of 0. That would be standard concentration for H plus would be 1 molar, which is a pH of 0. pH of 0 can get a little, can get a little dangerous. So a lot of times we'll run it at a pH somewhat greater than 0. Well, we might need to recalculate under those conditions, and we use that. Here's that Q again. This is the same Q that we worked with back in the equilibrium chapter. So this little 0 superscript means at standard conditions. Okay, so here we have delta G of a reaction is the delta G. I'll say it as, what I'm going to say is delta G naught, and the term that I'm saying there is NaUGHT. It's an I'll have to ask my wife about this to see if I'm correct, but I think that is an Old English term for 0. So delta G naught is the standard, and we want to calculate, well, what's it at our conditions? So delta G naught plus, there's your friend R again, T of the reaction, and natural log of the reaction quotient. There's your LNQ again. Be careful which R you use. I tend to use 8.314 joules per mole K here. That's a little different than the one we were using where it involved atmospheres. Notice there's no pressure term here because we're taking it into energy terms. Just be careful which one you're using because you want it in energy terms. You could do it in joules per mole K, or you could do it here. I've converted it to kilojoules per mole K. I hardly ever see anybody do this, but that is an approach that would be valid. Q is your reaction quotient, products over reactants, and then take the natural log of those. Well, so think about that and how delta G 0 means it's in equilibrium, right? And Q is the reaction quotient, so we could keep talking about this Q and moving it around until we can get delta G to 0. And that would look like an equilibrium constant. And in fact, that is how those are calculated in the first place. So if you look at, here's our delta G again. We want this to end up 0, right? Now we know delta G naught is going to be something other than 0, right? And we want to get K instead of Q. So delta G is 0. Okay. I'm going to do some algebra shenanigans, rearrange again, right? So you can think of subtracting RTLNK from both sides, or you can subtract delta G to get it over here and then multiply through by -1. Either way works. But so your delta G naught is equal to negative RTLNK, right? So now you can go from G to K, from K to G, etc., in order to figure out what your K values are. And then if you have multiple different reaction pathways to get to a final product, just remember that you add your delta G's together to get those. And remember that the N, the coefficient, matters. So you do multiply by it here. That's it for today. And so I'll see y'all in class. We'll practice calculating some of these.